Hi guys, we're going to start on 2.5a complex zeros. So this that I have up here looks exactly like your assignment. It is just with different questions. So we're going to go over a couple from each section. Um, so this is just asking us about complex zeros. So a complex number is, remember, a number that can have a real part and an imaginary part, but every number is actually considered complex because any real number can be considered having a zero for its imaginary part. So the first section just says to state the number of complex zeros for each function. It's kind of like asking how many solutions will it have. And we can always tell the number of solutions just by looking at the highest exponent. That will tell us how many zeros there should be. So on number 1, because the highest exponent is a 3, let me see why this is not writing. This one has 3 complex zeros, or 3 solutions is another word for it. On number 2, the highest one is 8, so that one would have 8 complex zeros. So if it's just asking the number of complex zeros, you're just looking for that highest exponent or the degree of the function, and that's going to tell you. So let's skip to the second part. It says, given the degree of the polynomial along with some of its zeros, find all the remaining zeros. So if my degree is 4, that means there has to be 4 complex zeros, right? But it's giving us 2, and these 2 that they're giving us are imaginary. So there's 2i and 3 minus I. So they are complex numbers that have imaginary parts. The thing about complex solutions with imaginary parts is that they always come in pairs. So if I have 2i as a complex zero, I know that the negative of that is also going to have to be a solution. Anytime you're solving an equation and you get imaginary solutions, they always come in pairs. The only difference between the two is that the sign in front of the imaginary part always changes to the opposite. So for 3 minus I, it's called a conjugate. The conjugate of 3 minus I is 3 plus I. Just the sign in front of I changes, not the one in front of the real part. So because I knew that 2i and 3 minus I were both complex zeros for this function with degree 4, I know the other two solutions are negative 2i and 3 plus I. So I'm finding those other zeros, but I don't really have to do any math. I just have to recognize that imaginary ones always come in pairs. So for number 6, the degree is 3, which means there should be 3 solutions or 3 zeros altogether. It's giving me 2. It's giving me negative 1, and it's giving me I. So I know there's one more. This one's just a real number, so that one will not have a conjugate pair. Only the ones with imaginary parts have them, and so I know that negative I would be that third zero. On number 7, there should be 6 altogether. It's telling me that there is the real number 2 with multiplicity 2. So remember, that just means that one happens twice. So I could either write 2 multiplicity 2, or I could write it as 2, comma 2. There's 2 of them that are both 2. There's 1 minus 3i, which means its conjugate pair 1 plus 3i also would be a 0. And then there's 2 plus 5i, which means its conjugate 2 minus 5i would also need to be there. So that would be 1, 2, 3, 4, 5, 6. So that's all 6 of our zeros. On number 8, we have, again, a degree of 6. So there should be 6 altogether. I've got a negative I, which means positive I should also be one of the zeros. I've got 1 minus I, which means 1 plus I should also be there. But that one says it is multiplicity 2. So that means that 1 minus I is actually happening twice. And so also 1 plus I would have to happen twice. There's 1, 2, 3, 4, 5, 6. So on these ones where it's giving you some complex zeros that have imaginary parts, it's really just asking you to recognize that they always come in pairs where the imaginary part changes sign. Um, on these examples, there was not one that had a negative in front of the real part. But if my imaginary or complex 0 was -4 plus I, its conjugate pair would be -4 minus I. So again, only the sign in front of I changes to the opposite. The one in front of the real part stays the same. All right, so let's go ahead and look at the next section. We have state the number of complex zeros and the possible number of real and imaginary zeros for each function. So it's basically still, it's not asking us to solve anything, it's just asking us to say how many complex zeros there will be, and again, that's just the degree. So like on number 9, there are 4 complex zeros. The second part of the question is just asking us, again, to understand that those imaginary zeros always come in pairs. And because of that, there's always going to be an even number of imaginary zeros. So they always have to be even if they're imaginary. The real ones don't have to be even. So what that means about this is that if there are 4 complex zeros altogether, all 4 of these are either going to be real or they're going to be imaginary. So it's asking how many possibly could be real and how many possibly could be imaginary. So it's asking just for the possibility. It's not asking for what's actually going on, just what could happen. So if all 4 of them were real, that would work. That would be fine. So it's, again, real plus imaginary should equal the total number of complex zeros. So if there are 4 real, that means there's 0 left to be imaginary. And you can have 0 imaginary, that's fine. If there are 3 real, if I had 3 real solutions, that means there would have to be 1 imaginary. But imaginary solutions always come in pairs. You can't have an odd number of imaginary solutions. So if I had 3 real, that would mean 1 would have to be imaginary. So that can't happen. We can't have 3 real because we can't have 1 imaginary. We could have 2 real and 2 imaginary because, again, 2 is an even number and those imaginary ones have to be even. If one of them were real, that would mean 3 would have to be imaginary. So again, that can't work because 3 is not an even number and imaginaries always come in pairs. And then 0. I could have 0 real and 4 imaginary. So the possibilities are that there could be 4, 2, or 0 real solutions, 0, 2, or 4 imaginary solutions, because these are the combinations that add to 4 that still give me an even number of imaginary solutions. So let's try number 10. So again, well, actually that one's the same. Let's go to number 3. So there are 3 complex zeros because my highest exponent is a 3. Okay, so we have real and we have imaginary that they should add together, keeping imaginary even. So if all 3 of them were real, that means I would have 0 imaginary, and that would be okay. If there were 2 real, that would mean 1 had to be imaginary, again, because these should add to this. Because I can't have 1 imaginary, that means I can't have 2 that are real. That won't work. I could have 1 real and 2 imaginary, and that will work because 2 is a positive, sorry, my screen. 2 is a even number. And then the other option is that I could have 0 real with 3 imaginary, but again, that one won't work because it's not a even number. So I could either have 3 or 1 real and 0 or 2 imaginary. Okay. So again, you're just trying to decide, keeping the imaginaries as only even or 0, how many could be real. Okay. The last section of your assignment, you're going to factor the polynomial as a product of linear factors, and then you're going to find all zeros. So linear means just x to the first power, right? So if you're factoring something to its linear factors, that means all of your x's in your factors should be just x to the first power. So we're just going to x factor here. So I've got a is 1 and c is -8. So these 2 numbers that should multiply to -8 and add to 2. So that would be 4 and -2. So this would just be x plus 4 times x minus 2 equals 0. So this right here is the product of linear factors. Remember, product means multiply, and linear factors are these, each of these in the parentheses is a factor, and they're linear because x is to the first degree on both of them. So this is the product of linear factors. Now to find the zeros, we know that we set each of these equal to 0 and solve for x. So the actual zeros would be 2 and negative 4. So 14 is pretty much exactly the same thing, so I'm going to skip that one. Let's look at number 15. So number 15, we have an x we need to pull out front. We have a common factor of x, right? So that would leave x squared plus x minus 12. Then we'll go ahead and x factor. So we have a is 1 and c is negative 12. So multiply those to get negative 12. And then b is equal to positive 1. So what multiplies to negative 12 adds to 1. I'm thinking 3 and 4 here with a negative 3. So the product of linear factors would be x times x minus 3 times x plus 4. So that's the first part. We just wrote it as a product of linear factors because all my x's are to the first degree. To find the zeros, we've got to set each one equal to 0 and solve for x. So x itself is just going to give us 0. That one's done. X minus 3 equals 0. I would add 3 to both sides to get positive 3. And x plus 4 equals 0. I would subtract 4 from both sides to get negative 4. So there's the actual zeros. On number 17, notice we have those 4 terms. So in this case, we would factor by grouping. Remember, if there is a negative between the two middle terms when we're factoring by grouping, we got to pull that negative inside and change that to a plus. So we don't inadvertently end up changing 11's sign as well and making the problem different. So here, x to the third minus 11x squared, we're going to pull out an x squared there, which will leave us with x minus 11. On the second one, because our x is negative, I'm going to pull out a negative x, which will make that x minus 11. Remember, if I multiplied negative x back in, I'd get negative x squared. Oops, not negative x, negative 1. See, good thing I checked. So pull out a negative 1. Negative 1 times x gives me the negative x. Negative 1 times negative 11 gives me positive 11. So I've got this common factor now of x minus 11, and so I'm going to pull that out front. And that's going to leave me with x squared minus 1. So now x minus 11, that's a linear factor. X squared minus 1, that one is not linear because our x is still squared. So we need to go one step further here. So there's a couple of things we could do. Because 1 is a perfect square, I could just go ahead and x factor this. I'm actually going to do it a different way though so that you can see how to do it if this were like, for example, a 3 or a 5, something that's not a perfect square. So x squared minus 1, I'm just going to set it equal to 0. And I'm going to solve for x. So I would add 1 to both sides here, and I would get x squared equals positive 1. And then I'm actually going to go ahead and solve this. I'm actually finding the x. So the square root of 1 is just equal to 1. And those cancel each other out. Remember, when you're taking the square root of a variable, you always have to do the positive and the negative of your solution. So x would be plus or minus 1. So if these are my zeros, then remember I can write those back as factors. For positive 1, it would be x minus 1, and for x minus 1, it would be x plus 1. So now this is actually the product of linear factors. I've got x minus 11, x minus 1, and x plus 1. And then the zeros would actually just be 11, 1, and negative 1. Okay, so if it's asking you to write it as a product of linear factors, it's asking you to write it out as all those x factors multiplied together, each of them being to the first degree. When it's asking you to find the zeros, it's asking you to set them equal to 0 and solve for x. So we're going to do one more example. Give me 1 second here. Okay, so now I've actually pulled up your assignment. This one is the one that you'll be doing for homework. I'm looking at number 17. That one is actually not going to be factorable, so we're not going to do that one. So cross off number 17 on your assignment. You don't need to do it. Let's see if I can get my marker to work here. Okay, you don't need to do 17. let's go ahead and try number 16 together. So again, it's grouping. So we're going to group the first two. We're going to group the last two. Because there's a negative between there, I'm going to pull that in, change that to a plus. So x squared plus 3x squared, I'm going to pull out x cubed plus 3x squared. I can pull out x squared, which leaves x plus 3. 3x minus 9, well, it's negative 3x minus 9, so I'm going to pull out a negative 3. And that's also going to leave me with x plus 3. Again, that's because I pulled out a negative 3, so that will change the sign here, because negative 3 times x is negative 3x, negative 3 times 3 is negative 9. So now I see that I have this x plus 3 in common. So I'm going to pull that x plus 3 out front, which would leave x squared minus 3. So this is not quite a product of linear factors yet, because this x right here is still squared. So that's where you're going to take that x squared minus 3 and you're going to set it equal to 0. You're going to solve for the x. So add 3 to both sides gives me x squared equals 3. And then take the square root. Okay, so square root of 3 is not going to simplify, but I do need to have the positive and the negative in front. This is actually the zeros, but to write it as a product of linear factors, if my 0 is positive square root of 3, my factor would be x minus square root of 3. And if my factor is negative square root of 3, my factor would be x plus the square root of 3. So that's what I'm talking about. If that's not a perfect square, you're going to have a square root in your example here, in your factor here, but that's fine. And then your zeros here would be x equals negative 3, x equals square root of 3, and x equals negative square root of 3. So I guess we kind of did that a little bit backwards. We found the zeros first and then wrote them back as linear factors. But because it said to write it as a product of linear factors, that's why we needed to do that. All right, guys, good luck and have a lovely day.